All right, guys, so today's lecture is on spectroscopy. We're going to talk about the electromagnetic spectrum a little bit and the Beer-Lambert law. Okay, so the first thing is to understand what spectrophotometry is. Okay, so this is an analytical tool where you can find concentration. Okay, so now we're in the unit called solutions, right? So we need a tool to be able to find out what the concentration is of a particular solution, what the molarity is, okay? So spectrophotometry uses light to measure chemical concentrations, okay? So it uses specific wavelengths of light. Okay, so you have a light source here, okay? And now, particular to the color of the solution you're dealing with, they pick a certain wavelength of light. So the wavelength has to do with the actual solution. Okay, so you pick a wavelength of light depending on the solution. Okay, it goes through what's called a cuvette. Okay, and a cuvette is almost like it's like a square test tube. Okay, where the light goes through it. Okay, and then there's a detector, obviously, that reads an output. Okay, and you're measuring the absorption of the light through the solution. So the higher the absorption, okay, the higher the concentration of your solution. And it's related, the data is related through what's called the Beer-Lambert law. Okay, so A is for absorption. Okay, E, or the sigma, or I guess epsilon, excuse me, is what's called the absorptivity coefficient. And that's for a particular solution. So every particular solution, like if it's copper nitrate or Kool-Aid or potassium dichromate, it has a particular absorptivity coefficient. Okay, so that's dependent on the solution. And then, of course, there's a certain path length L with which the light travels, and that's dependent on the cuvette size. Okay. And then C, little c here, is your concentration, which is what you're looking for. Okay, so you can see that A and C are directly related, especially if E and L are constants. Okay, and if you look at, here, I'll show you this in a minute, but if you construct a curve based on your data from a spectrophotometer, you can see that it is a linear line increasing with increasing concentration. So concentration goes on the x-axis, absorbance goes on the y-axis, okay? And you can see that the slope of the line would be this multiplication of the absorptivity coefficient and the path length, which are constants. So you can actually calculate the slope of the line to calculate epsilon and the little l, the path length. Okay. And in your lab today, you're going to be doing this. You're going to be playing with wavelength. You're going to be playing with cuvette length. You're going to be playing with different chemicals to understand how a spectrophotometer works. It's a really good lab. I did the whole thing before you guys came to class, and it was really interesting. Now, I just want to talk about one thing you're going to see in the lab, and that's how they pick the wavelength of light. Okay, so they pick the wavelength of light to shine through the cuvette based on really the color of the solution. Okay, and I don't know if you remember the color wheel from like elementary school, but remember it's the color you see, like so for example, if a solution's yellow, is the opposite of the color that's absorbed. Okay, so if the color you see of a chemical is yellow, what they're going to do is pick a violet wavelength of light to put through, because that's what's going to be absorbed. Okay, so the opposite color on the color wheel is what gets absorbed. The color you see is the one that's transmitted. Okay, so that's how they pick the wavelength of light. So this color or wavelength, which is in nanometers, is picked based on the color of the solution, okay? And you're going to see all that, which is pretty cool. Okay, now one thing too that you have to know in AP, okay, and it's not a lot, okay, but different types of electromagnetic radiation, okay, have different responses when the molecules absorb the light. Okay, so if different types of molecules absorb the light, they have different responses. Okay, so if you put microwaves on a molecule, all that's going to happen is the molecule will be able to rotate. Okay, so that's what's happening in microwave ovens. Okay, you're rotating you can see the little rotation here, little rotation arrows. They're rotating. If you put infrared light, okay, this wavelength of light, they will just vibrate, right? Go up and down. Okay, that's what happens. Okay, ultraviolet will get them very excited, and then X-rays, you'll start breaking, bond breaking, and ionization. Okay, so it's important to know these three, I think it's just these three, these are together, these three types of responses. Microwave has rotation, infrared has vibration, visible, ultraviolet, and X-ray are, you're starting to get electronic excitation. How do I say that? Excitation. Okay, and here it is again in just a different form. Okay, you can see that lower frequency has a longer wavelength, higher frequency has a shorter wavelength. We're talking like gamma waves up here. Okay. And rotational is microwave, vibration is infrared, and I think we just need to know the electronic transition, which is near UV. Okay. And that's it.